All right. Hi, my name's Keone Han. I'm the co-founder of Monad. I'm going to be giving you a really fast lightning talk just to give some information about what we do in Monad to accelerate EVM execution. All right, so what is Monad? Monad is a new EVM layer 1 offering both performance and portability. We offer over 10,000 TPS of throughput, aka a billion gas per second, 1 second block times, and 1 second finality. Monad also offers full bytecode EVM compatibility so that any EVM app can be redeployed on Monad without any changes. Why is this important? This is important because we want both decentralization and performance. Monad has hundreds of nodes in consensus, so hundreds of nodes ultimately contributing to block production and minimal hardware requirements, specifically 32 gigs of RAM. And it's important to have really low hardware requirements so that anyone can run a node and have access to the full state and be able to consult the exact state of the world at any given time. All right, so I'm going to talk about 3 major concepts here. The first is asynchronous execution. The second one is parallel execution. And the third one is MonadDB, enabling parallel state access. So first of all, asynchronous execution. Just to give a little bit of background, blockchains mostly have interleaved execution. And apologies for the legibility here, but consensus and execution are interleaved. And what this means is that because consensus is quite expensive, it takes up most of the block time. Therefore, execution can only be a small portion of that time. So just to take Ethereum, for example, Ethereum has 12-second block times, but in practice, the actual execution budget is only 100 milliseconds. So this is crazy because that's literally only 1% of the total block time. And I always like to think of it similar to how people say that you only use 10% of your brain. What if you could use 100% of your brain? Think about how much smarter you could be, how much more you could do. And the reason that this execution budget is so small is because consensus and execution are interleaved, and consensus is taking up most of that time. All right, so here's a simple schematic. Execution is the dark block, and consensus is kind of the light block. And you could see just an example of a couple of blocks proceeding one after the other. And here's another schematic, which is kind of showing the same thing, but through time. Asynchronous execution is the idea of moving execution out of the hot path and only doing consensus. So basically having all these nodes agreeing on the official ordering of transactions without executing, and then after consensus completes, then 2 things can happen in parallel in separate swim lanes. The first is consensus over the next block, and the second thing is execution over that list of transactions that we've just agreed upon. So kind of now the schematic looks a little bit like this, and I've just updated that other schematic that we have. So initially when we look at this, it doesn't really look that different. We're not getting that much more out of it. We've reversed the order, so now execution happens after consensus, and consensus on the next block can proceed while execution is proceeding. But the important thing to note here is that now that we've changed the architecture, we can actually expand that dark blue block, the execution portion, and have a much larger execution budget. So yeah, just to summarize, asynchronous execution is the concept of running execution post-consensus while consensus on the next block is proceeding. There's a couple of smaller, finer details that we need to cover in order to make this possible. So in particular, every node is executing that same set of transactions in parallel independently. So we have to do some special checks later to make sure that they all got the same result. And then note also that the nodes are coming to consensus with a slightly delayed view of state. So we need to do some special stuff to make sure that we're always safe. But in general, this change is a massive improvement for the overall throughput of the system because we have so much more time to execute. All right, the second thing to talk about is parallel execution. So just to emphasize, in Ethereum, transactions are linearly ordered and they're serially executed in most systems. And the goal is to still have transactions be linearly ordered, but do something smarter so that we can get to the end state of that long list of transactions, get to that same end state as if we'd executed serially while doing something smarter. And so parallel execution is actually a very simple algorithm. There's some fancy names like optimistic concurrency control or software transactional memory. But I think the thing I want everyone to know is that the actual algorithm is something that is just very intuitive, that we all kind of intuitively understand. I'll walk through it right now. Just doing the intuitive thing. So basically, really fast, optimistic parallel execution is the idea of running many transactions in parallel as if they were starting from the same starting point and generating a bunch of pending results. And each of those pending results is a list of the inputs and outputs for that transaction. And so we generate a bunch of pending results all at the same time while running a bunch of transactions in parallel. And then we step through those pending results in the original order of the transactions. And for each pending result, we look at the inputs. And if those inputs are unchanged since the point when they were executed, we just commit that pending result. And if they've changed, then we go re-execute. So I think maybe to help understand this a little bit better, I want to do a really simple example. So imagine that we have 5 transactions. And so just the serial way would just be doing them one after another, all in the same core. And the smarter thing is to run them on separate cores. And as soon as the core frees up, then start doing another transaction. So we generate some pending results from this algorithm. And so let's take an example. Let's say that let's say there's 5 transactions that we'll focus, actually 3 transactions we'll focus on. So the first one is me sending Alice 100 USDC. The second one is Kobe minting an NFT, something totally unrelated to my USDC. And then the third one is me sending Bob 100 USDC. So we run these 3 transactions in parallel. Oh, and sorry, one thing I should have said before is that say that the starting state is that I have 1,000 USDC and Bob and Alice both have 0 USDC in their account. Okay, so we'll go through this example. So in parallel execution, what happens is we run all these transactions in parallel, and you can see that we actually get some bad results. So in particular, if you look at transaction 1's pending result, it starts with an input of me at 1,000 and ends with me at 900, which is correct. But then if you look at transaction 3's pending result, it also started with me at 1,000 and ends with me at 900, which is of course wrong. So, but we generate these pending results, and we're going to sort of deal with any conflicts a little bit later. So we'll step through these pending results. The first one, which starts with me at 1,000, goes to me at 900, and starts with Alice at 0 and goes to Alice at 100. This is totally fine, so that we can accept this one. The second one is totally unrelated stuff, so this is fine. We can accept this one. And the third one is bad because it had a bad input relative to what our new view of the state of the world is, which is 900 USDC for me. So we need to go reschedule this work. So, we're just going to go and re-execute transaction 3 on whatever the most free core is. And the thing to emphasize here is that this re-execution is actually very cheap because the state that was needed for this transaction is already in memory, and almost all of the execution costs are actually just reading state from SSD. So because the state is in memory, it's very fast to re-execute. Okay, so when we re-execute, now the input is me at 900 and the output is me at 800. So this is now correct. So now we can accept this and then just keep moving onward. So just to emphasize, that's the end of the example, by the way. Like, that's literally all that this algorithm is. It's not anything crazy. It's just the intuitive thing. So just to emphasize, running many transactions in parallel, generating pending results, keeping track of the inputs and outputs for each one, committing them in the same order that they were originally defined in, and re-executing if we needed. And just to emphasize, every single transaction in this algorithm will end up getting executed at most twice. Like once during the parallel run, and then maybe once if it needs to be re-executed. All right, so the most common question that we actually get with respect to this algorithm is what happens if there's a whole bunch of transactions that all have sort of like serially dependent state. So for example, if I send 100 transactions of me sending USDC to different people, then clearly these are all going to be serially dependent. So we're going to have to re-execute transaction 2 through 100 again. And so it's actually not a big deal. And the reason why this is NBD is because the first execution is pulling those state dependencies from SSD into cache. And then once we do that, then all of the other executions are going to be quite cheap. The second execution is fast because the state is cached. So you can think of optimistic parallel execution as two phases, where the first one is running many transactions in parallel. This is slow, but it's in parallel, so we're doing many transactions worth of work, pulling many transactions worth of state in. And then the second stage is fast because we already have all the dependencies in cache. So all of this is dependent on one very crucial problem, which is that we need to be able to pull a lot of state from the SSD in parallel during that parallel stage. So this is actually a perfect transition for the third and final part of Monad that I want to talk about, which is parallel state access. So I'm going to pause here for a second because I feel like I've given a lot, sort of like a wall of information. I just stop and think for a second about the world that we live in and how advanced hardware is now. Like, we all know that GPUs are incredibly powerful. They've enabled like a revolution in terms of machine learning. The same thing is actually true in terms of SSDs. SSDs are extremely powerful, and they're very cheap. So you can buy a 2 terabyte SSD with really high IOPS, so high number of I/O operations per second, about 1 million I/O operations per second for about $200. It's really cheap. Basically, you can think of SSDs as being big, cheap sources of storage that actually are a bottle with a really big, wide bottleneck. So there's a lot of bandwidth to SSDs. The only problem is you need software that can actually take advantage of this really wide bottleneck. So it's really important to saturate that wide bottleneck that's out there. And the problem is that in Ethereum clients right now, they really don't use this bottleneck well at all. I should say neck of the bottle rather than the bottleneck, actually, because it sounds like a blocker. So Ethereum lives in a Merkle-Patricia tree, and then that Merkle-Patricia tree in most clients is embedded inside of another database. In the case of Go Ethereum, it's LevelDB or PebbleDB. And then both of those databases actually use another tree structure under the hood. So for those of you who are familiar with the Merkle-Patricia tree, you know that there's like data that's stored at the bottom of the tree in leaf nodes, and to traverse to any of those nodes, you have to traverse all the way through the tree. And the problem is that because each of those nodes is stored in another tree structure under the hood, there's like a second lookup into a tree that's happening for each node that you visit. So you're kind of doing almost like a quadratic amount of work to navigate down to one node. This is suboptimal. This data structure is embedded in another data structure. And so this means that there's a lot of sequential lookups. I believe that to look up one value inside a Merkle tree that's stored inside of LevelDB or PebbleDB, it's about 50 sequential operations. It's 50 sequential operations just to go get that one value. And so you can imagine that this means that it's really slow to access data from the SSD in a normal Ethereum client. So how did we solve this problem? We introduced a custom database called MonadDB. This is a custom state store that stores Merkle-Patricia tree natively on SSD. This avoids this read amplification problem that I mentioned before, where we're kind of like doing a quadratic lookup. Instead, we're just directly navigating to a node in the Merkle tree. In addition, we have support for asynchronous I/O using IOU ring. And we also bypass the file system for additional improvements. Just in general, this is a really efficient way to access data, and that allows many transactions running in parallel to all read from the database effectively in parallel, thus enabling parallel execution to be performant. All right, so just to give a recap, Monad is a high-performance EVM layer 1. And the reason why this is important is because it enables decentralization plus performance. Anyone should be able to run a Monad node with minimal RAM requirements. It doesn't rely on a lot of memory because of MonadDB, which is allowing the SSD to be utilized much more efficiently. And Monad is able to accomplish this through these couple of architectural software improvements rather than relying on hardware. So lastly, I just wanted to say a couple of words on why this matters. This matters because all of us here understand the transformative power of decentralized currency and decentralized applications, but we need to actually scale those to hundreds of millions of users. So if you think about, just doing some very simple math, 100 million daily active users doing 10 transactions per user per day is a billion transactions per day. I always like to talk in transactions per day because I think you can reason more clearly from more of like a traditional tech perspective. But yeah, 100 million DAUs is like not crazy. That's not a crazy level of adoption, but that would correspond to a billion transactions per day, which is 10,000 TPS. So, all of our goals here, I think, at the conference is to see the adoption of cryptocurrency more widely, help crypto apps eat the world, and we need better infrastructure in order to be able to do that. Thanks so much, guys. Appreciate it.